So today we're going to dig into a really big question in AI. How do these huge models actually learn? Are they genuinely understanding things, or are they just getting really, really good at memorizing? Well, some researchers designed a brilliant set of tests to find out, pitting two major training methods against each other to see which one truly teaches an AI how to think.
You know what I'm talking about, right? We've all been there. You stay up all night, you just jam your brain full of facts and figures, and you just hope it sticks long enough to get you through the exam. You're not actually learning the subject, you're just learning the test. Well, it turns out AI can fall into that exact same trap. A model can be fed so much data that it ends up just memorizing the right answers to questions it's seen before. And that gives this illusion of intelligence, but without any real deep understanding underneath. And that, right there, is the million-dollar question. It's exactly what this research is all about. How do we get from a machine that memorizes to a machine that can actually reason?
Okay, so this gets us to the core challenge that researchers are up against. How can you even tell the difference between an AI that's just memorized a bunch of answers and one that has actually learned the principles behind them?
To figure this out, they basically staged a showdown. They took two of the most common methods for training these big models and threw them into the ring against each other, using a series of really clever tests designed to expose which one was the real thinker and which one was just the memorizer.
All right, so let's meet the two contenders in this. Let's call it an intellectual cage match. In one corner, we have Supervised Fine-Tuning, or SFT. And in the other corner, we have Reinforcement Learning, or RL. Okay, so here's the simplest way to think about it. SFT is kind of like studying with the perfect answer key. You see a question, and you're immediately given the perfect answer. RL, on the other hand, is all about learning through trial and error. You try something, you see if it works, and then you adjust your approach for next time.
Let's dive a little deeper into SFT. This method works by showing the model thousands and thousands of high-quality examples. Here's a question, here's the perfect answer. Here's another question, another perfect answer. The paper actually calls it a format teacher because it's fantastic at teaching the model what a good response is supposed to look like. Now, reinforcement learning is a completely different beast. Here, the model generates an answer, and then a totally separate system called a verifier checks the results and gives it a score. You get points if you got it right, you lose points if you got it wrong. It never gets the answer key. It has to figure out how to solve the problem all by itself. So, we've got our two methods. Now, how in the world did the researchers design a fair test to see which one actually teaches the AI to reason? Well, they built two custom challenges from the ground up. First up, we have a card game they called General Points. The AI gets shown 4 cards, and its job is to use basic math, add, subtract, multiply, divide, to hit a target number, which is usually 24. It's just a pure test of logic and arithmetic skills. Then, for the second test, they drop the AI into this virtual city navigation simulator called VIRL. It's given text instructions, and it has to find a specific destination. This is all about testing its ability to understand spatial directions and follow complex, multi-step commands. But here's the kicker. This is the really clever part. For both of these games, the researchers trained the AI on one set of rules, and then they tested it on a completely different set of rules that it had never, ever seen before. This is the ultimate test of generalization. Can it actually adapt, or does it just break when you change the game? And now for the results. This is where things get really, really interesting, because when the rules changed, one of these methods adapted beautifully, and the other one just, well, it completely face-planted. Just take a look at this graph from the navigation test. The dashed lines show how they did on the rules they were trained on, and you can see both methods do pretty well. But the solid lines, that's their performance on the new rules. Look at that red line for SFT. It absolutely craters. It just collapses. But meanwhile, that blue RL line just keeps on climbing. And this chart here really just drives the point home, right? This was the core finding across all the experiments. When it was faced with something new, the reinforcement learning model figured it out and succeeded. The SFT model, which had only memorized the old training rules, failed spectacularly. I mean, the researchers themselves put it pretty bluntly and clearly. The bottom line is this. RL learns the principles, the underlying rules of the game. SFD just memorizes patterns. And when those patterns change, memorization becomes totally useless. But hold on, because the story doesn't end there. Just when you think you figured it all out, and that SFT is a bad guy here,
the researchers discovered something completely unexpected. It turns out that reinforcement learning, on its own, is a terrible student right at the beginning. When they tried to train a model with just RL from the very start, it learned absolutely nothing. It just couldn't get off the ground. It needed some sort of primer, a foundation to build on.
And this is where SFT makes its triumphant return. The winning strategy, the secret sauce, is a two-step process. First, you use SFT, our format teacher, to teach the model how to speak the language of the problem, how to structure its thoughts and its answers. Then, you bring in RL to build on top of that structure and teach the model how to actually reason.
So SFT and RL aren't enemies in a fight for the top spot. They're actually partners, working together. SFT provides the form, the structure, and RL provides the function, the reasoning. You absolutely need both to create an AI that can truly generalize and adapt. And how well does this partnership actually work in the real world? Well, this number says it all. By using their combined SFT then RL approach, the researchers didn't just prove a theory, they built a model that absolutely smashed the previous record on that VIRL navigation benchmark. It improved performance by that massive 33.8%. Now that is the power of true generalization. And this all leaves us with a final, huge, and fascinating question for the future. This study shows that the path to more capable reasoning AI involves letting these models learn from their own mistakes. But that raises a much bigger question for all of us. As we build these increasingly powerful systems, how do we create the safe spaces, the sandboxes they need to learn before we let them out into the real world?